This is Lab 4, dealing with circuits. Here's a brief table of contents for the lab. We'll have an introduction, including the purpose of the lab. We'll look at the physics principles used. We'll observe in detail part 1 of the experiment and part 2, showing the procedures and results. Then we'll discuss our what-if scenario and move into our conclusion, including possible sources of error in the experiment. So the purpose of this lab was to examine series and parallel circuits in a simulator to visualize the effects of resistors and capacitors. This lab explores the time-dependent voltage and the current in a DC current. And we also use multimeters to predict the potential differences in the circuits and the changes in a circuit as time passes. Some goals was to create a series circuit to test energy and current conservation, to create an RC circuit to use a capacitor and apply energy conservation once again, and then graph the results and find an RC value to compare to the theoretical value. And then a brief overview of our results. We saw that the calculated values in the experiment match the theoretical values within a reasonable margin of error. So the principles used, we see the series versus parallel connections in the diagram to the right. We also use both conservation of charge and energy and the conservation of current with the loop rule and the node rule. We use Ohm's law, and then the principles of capacitors, resistors, and ammeters. As capacitors store electrical energy in an electric field, resistors slow down the current and decrease the voltage, and then ammeters only measure the current. They don't change the flow of the circuit. So part 1 was dealing with series circuits, which had included a simple circuit with two 1.5 volt batteries. And we calculated the I value here, which was calculated to be 0.02 amps. And then when inserted backwards, the ammeter reads the value of opposite and equal magnitude, negative 0.02 amps. When the ammeter is replaced by a voltmeter, the ammeter shows 0 amps because the circuit is open, and the voltmeter has high resistance, so there's only a very small current running. Therefore, the ammeter cannot measure it. With the voltmeter, the delta V value is 3 volts. Since there's no current, there's no potential value for the resistors. Only the battery is shown, which has a potential difference of 3 volts, 1.5 per battery. And as you see in the diagram here, which shows the potential differences between each point across a discharging capacitor. As you see, the values from each point, and then for a sum of potential differences to be 0. Next, why doesn't the addition of the voltmeter change the ammeter reading? This is because it has a very high resistance, allowing very little current to flow through. When connecting the voltmeter across a 100 omega resistor, the ammeter reads 0.02 amps. And then if we were to replace the voltmeter with an ammeter in parallel with the 100 omega resistor, the ammeter reading increases to 0.06 amps, which is due to the parallel series avoiding the 100 resistor. And then you see below the calculations for the potential difference of the circuit using Ohm's law, each element. Next, part 2, we saw a battery, capacitor, and a 10 omega light bulb connected in series, which sees the light starts bright and then becomes dimmer, and the same is true when the battery and capacitor are disconnected. When the battery and the capacitor are connected with the 10 omega bulb, the charge time is 8.9 seconds and the discharge time is 9.4 seconds. Similarly, with the 20 bulb, the time to charge is 18.3 seconds, and the time to discharge is 18.5 seconds. Next, we see the time-dependent voltage across a discharging capacitor in the RC circuit. Our predicted value, which was calculated to be 6 seconds, actually matched the actual value calculated of 6 seconds. As you see here in the graph, we have the natural log of V over V naught versus time graph, which displays a nice linear graph of our predicted value. For the what-if scenario, what if we were doing this lab in real life and use an actual ammeter instead of an ideal simulated? The current would be lower since the ammeter would have resistance. This is different from the simulation used in the lab. Next, what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly our ideal model predict the capacitor to reach full charge? The ideal model, including the capacitor, would be able to reach full charge immediately, which is not realistic in the actual model since there's only a small amount of resistance existing between the wires and the batteries present. So in this lab, the main source of error in the experiment was the timing. The experiment required precise timing and recording of the voltage, and there was likely user error in both attaining the optimal time interval to record the data and the actual observing of the circuits. And then some points to end on. The online simulations don't represent real circuits, as real circuits always have more resistance, which lowers the current and the voltage. Similarly, capacitors are a useful way to absorb, to store, and release energy into circuits. And then this calculated RC value is an important value indicating the time it takes to charge a capacitor, as we saw in part 2 of the lab. And lastly, the conservation of current. Current is the same everywhere within a circuit. Thanks.